Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing transition metal olefin complexes over the last few lectures. Particularly in the last lecture, we have looked at various kinds of reactivity and bonding of transition metal olefin complexes. In particular, we have looked at how the bonding affects the reactivity of this kind of complexes, and these, as has been mentioned earlier, are very important intermediates in many catalytic cycles. For example, hydrogenation, metathesis, polymerization reactions, oligomerization reactions, and so on and so forth, isomerization reactions, and hence it is important to study the chemistry of transition metal olefin complexes. So, with that, in this lecture we are going to look at the reactivity of transition metal olefin complexes in more details. Now, these olefins when they bind to transition metals, undergoes two kinds of interaction. One is ligand to metal sigma interaction, as well as transition metal to ligand pi back donation. And this we have discussed in the previous lecture, but what happens is, as a result of this dynamics of these two interactions, the charges at the transition metal as well as the ligand carbons gives a vital clue as to the nature of this interaction. For example, if there is predominance of sigma donation, then the transition metal would be less positively charged and the ligand would be more positively charged, because there is a loss of electron density and there is a gain on electron density at the transition metal. And for example, if there is a predominance of pi back donation, then the ligand electron density would increase, whereas the electron density on metal would decrease. And thus, by looking at the calculated atomic charges, one can guess an idea as to the nature of this forward sigma donation and backward pi donation that occur in these complexes. And this can be computed using quantum chemical calculations, using simple DFT methods, where one can have an idea as to the charges, atomic charges on each of these fragments and moieties. So, for example, this bis alkene nickel bisamine complex in H2 twice, the oxidation state of the nickel is in +2 state. Okay. The charges on nickel, alkene and amide moiety, which is a negative NH2 minus, the computed charges are nickel being +2, it is not really +2, it is +0.83, and for the alkene, since it is sigma donating, there is a loss of electron density from the alkene, and it is almost 0.02, and for the amide, which is a monoanionic ligand, this is not really -1, it is -0.43. So, what one sees that the computed charges at the atom are less than what the calculated charges based on the oxygen state would lead to, and that is understandable in the sense that oxidation state is a formal concept where complete charge separation of the bonded electron is assumed when calculating the oxidation state of the metal. So, even though nickel is formally a is in +2 oxygen state in this complex, the real charge or computed charge in the nickel is only +1 or 0.83, and similarly the amide ligand, which is supposedly -1, but the computed one is even less than half than that, and it is -43, and for alkene this is 0.02. So, now if one goes from nickel 2 complex to a nickel 0 complex, for example, instead of bis amido, if there is bis alkene, bis amine C2H4 nickel NH3 whole 2. So, now there is 2 ammonia instead of 2 amido, then the charge on the nickel, this is a nickel 0 complex, the charge on the nickel is plus 0.58. So, it is not really 0, that means that a considerable amount of back donation has happened on nickel, and the pi accepting ligand is since the pi acceptor ligand is alkene, then the alkene sort of got this electron density from metal. So, that means the predominance of this transition metal to ligand pi interaction that happens. As a result, the alkene has become negative now, and the metal has become positive. So, it is no longer 0, but it is 0.58, because now electron density has moved from transition metal onto this alkene ligand, which itself has become negative, and ammonia moiety, which is NH3, has slightly positive because of just sigma donation from ammonia to the ligand, and it stands at plus 0.11. So, what one can see is that if one were to compare nickel 2 and nickel 0, nickel 0 is more electron rich, and hence nickel 0 has greater transition metal to alkene by back donation. As a result, alkene moiety in nickel 0 complex is more negatively charged at minus 0.78, whereas in case of nickel 2 the metal center is less electron rich. As a result, nickel to alkene back donation occurs not much, and hence that alkene is no longer negative, and it is slightly positively charged. Probably in that case the back donation is almost negligible or does not occur at all. So, these charges gives a nice view or insight about the extent of ligand to metal sigma donation and metal to ligand pi back donation, as elucidated by these related complexes which contain alkene, nickel bis amido, where nickel is in +2 oxidation state, and alkene nickel bis amino, where nickel is in 0 oxidation state. So, we are going to sort of look at these metal ligand and ligand to metal interaction in olefinic complexes in much more details as we discuss a few more examples in this particular regard. Now, the molecular orbitals are originating from the interaction of the olefin with the metal is constructed by symmetry matched MOs are formed by symmetry matched combinations of metal and ligand orbital. So, the energy of the transition metal olefin bond is dominated by of Tm bond is dominated by metal to ligand pi back donation. Contribution. Now, this is an important statement given the fact that this metal to ligand pi back donation results in multiple bonding character of the transition metal olefinic bond, because now over and above the sigma bond that is formed, the back donation gives the multiple bond, the pi bond in addition to the sigma bond, and as a result the energy of the transition metal olefin bond increases. So, the energy of this transition metal olefin bond dissociation energy is dominated by metal to ligand pi back donation, and that is a very crucial information, because then one can look at the transition metal olefin bond dissociation energy and have an insight as to the extent of forward donation, forward sigma donation and backward pi back donation that is occurring in these complexes. And also the another important aspect of this to forward sigma donation and pi back donation is the fact that olefin to metal sigma donation and metal to olefin pi back donation both weakens the intraligand CC double bond. The reason being that in the first case, where the pi electron is donated to the transition metal, then the CC double bond is weakened. Now, in the next case, when there is back donation, then obvious as the donation happens on the pi star orbital, then that sort of tries to give the cyclopropane intermediate, where this double bond has weakened or even cleaved. So, what it says that both the interaction, the forward as well as the backward donations significantly weakens the carbon carbon double bond. Now, let us take an example of how this really affects, and what we saw that in both cases the CC double bond is weakened, and let us take a look at some of the experimental examples for the same. For example, let us say if it is free C2H4, then new C11C centimeter inverse is 1623, and let us say if it is B alkene C2H4 whole to Ag BF4, then because of both of these interaction it is 1584. Let us say then another complex C2H4 whole to rhenium CO4 PF6, this is 1539. Then C2H4 PdCl2 dimer is 1525. Cp Mn CO2 C2H4 is 1508. Cp rhodium C2H4 whole 2 is 1493, C2H4 Fe CO4 is 1551, then Cp Fe CO2 C2H4 PF6 is 1527, and the one that is ice salt KPtCl3 C2H4 H2O is 1516, and the last one is C2H4 PtCl2 is 1506. Now, what we see is that all of these are starkly at lower energy than that of this free alkene, which is way much at higher energy. So, that means that CCC double bond C is more strong for free alkene than when it is bound to transition metal complexes. Now, another instance which sort of comes out by looking at the table is all of these are late transition metal complexes. Now, that sort of makes sense in the sense that sort of indicates that the for early transition metal, the metal to ligand back donation is not very strong. That makes sense because for early transition metal, the metal to ligand pi back donation is not strong or weak, and as a result early transition metal does not, consequently early metal does not stabilize pi acidic ligands like C2H4. So, that is a very interesting observation in the sense that in absence of the metal to ligand back donation, it is very difficult to have a transition metal olefinic complex. So, just simple sigma donation for the ligand to transition metal is not sufficient enough to stabilize olefinic complexes, and that metal should be electron rich enough to participate in metal to ligand pi back donation, otherwise the olefinic complexes would not be stable. That is the second observation. So, in all cases what it seems that both of these forward donation and backward donation significantly weakens the CC double bond, intraligand CC double bond, resulting in the CC frequency appearing at lower energy. Now, these complexes have been characterized structurally not only by proton X-ray diffractions, but also using neutron diffractions, and hence more accurate data sort of exists. So, to begin with, we are going to take up some examples of this. To begin with, let us take a look at this Zycel salt, which is KPtCl3. So, the structure is PT Cl, 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 and this is a anion. Now, what is observed is that there is loss of permeability planarity of olefins. Upon coordination with metal, and the CC bond length is 137 picometer, similar to uncomplexed free olefin, which is 135 picometer. Now, what it means is that this is a very weak adduct of the olefin bound to the transition metal. Olefin, the structure also says that olefin is perpendicular to PTCl3 plane, and because of this trans effect, the PTCl bond trans to olefin is elongated, and H1 H4 and maybe highlight this H1 H4 and C1, and this one is C2 are not coplanar. And the angle between two CH2 planes is 146 degrees. So, here is a nice example where one can look at the structural parameters of the olefin after it binds to the metal center, and this has been done by the structural characterization of the Zeiss salt, where we saw that there is a loss of planarity of olefin upon binding. CC bond length has slightly increased from 135 picometer to 137. Olefinic CC bond is perpendicular to the PTCl3 plane, and lastly is that the chlorine, which is trans to the olefin, is slightly elongated as a result of the trans influence. Similarly, look at another example. This is for Cp rhodium, C2H4 and C2F4. So, here there are two olefins be bound, one is C2H4, the other one is C2F4. So, here is this rhodium bound to four fluorines, and these are olefin containing two hydrogens. So, CC bond between the two hydrogen is 135 picometer, and for the rhodium fluorine one, this is 140 picometer. So, there is elongation that happens in the CC bond. Rhodium CC bond length containing two hydrogens is 216 picometer, rhodium C bond length containing 2 fluorine is 202 picometer. So, what it says that there is loss of planarity of olefins and C2F4 binds more closer than C2H4. C2F4 distance is 202 picometer and C2H4 is from rhodium. So, this is about 216 picometer and this is 202 picometer. Now, reason that C2F4 is more tightly held because in C2F4 this rhodium to olefin pi back donation is more, and this interaction can be represented as C2F4 pi is more than the rhodium to C2H4 H4 pi back donation, and that is because fluorine is more electronegative, than hydrogen. Okay. So, what we have seen over here is that fluorine being more electronegative, the metal to ligand pi back donation is more acute in the C2F4. As a result, C2F4 is more tightly bound, closer to rhodium about 202, and because of the more back donation, the CC bond is almost like a single bond character at 140 picometer, and because of the less back donation, the CC bond is shorter for the C2H4 moiety. So, this is not only reflected in the proximity, but also lifted in the CC double bond, and a very nice example where competing olefin, one more electronegative than the other, compete for electron density, and the more electron deficient olefin takes on more back donation from the metal. As a result, it is bound more tightly than the corresponding hydrogen counterpart. So, with that, I would like to conclude the discussion that we have had in today's lecture, where we have looked into the reactivity of transition metal olefin complexes, particularly with respect to the sigma donation and pi back donations, which are reflected in the atomic charges, as well as the characterization that are involved by IR, where one can look at the CC double bond, and from the extent of the decrease in CC bond double bond to the lower energy, one can sort of guess to what extent this forward sigma donation or pi back donation has happened. We had also seen that these olefin complexes are sort of stabilized by late transition metal, which are capable of undergoing metal to ligand pi back donation, and for early transition metal which does not have much electron density, olefinic complexes are very difficult to make. And then we have seen structural characterization of two important olefin complexes. One is a platinum complex containing olefin, which is the initial Zeise's salt, where we saw that olefin loses planarity upon coordination, and also we have looked at the bond lengths and bond distances. And the next one is a very interesting example of rhodium, where the rhodium is bound to two olefins, one very electron rich, another electron poor, and what we saw that the electron poor olefin has competes for the electron density because of the electron negativity of fluorine substituents. It grabs more electron density in form of metal to ligand pi back donation, and as a result it is more tightly held or more closely held towards the by the metal, and also it is reflected in the CC bond length, which it has more like a single bond character. So, with that I would like to conclude today's lecture, which was on transition metal olefin complexes and its reactivity, and we are going to discuss more on it, particularly the reactivity aspect in the next lecture. Till that time, goodbye and thank you.